Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everybody. It is a pleasure to have Olivier Pierre. I botched your name. I thought I could do it right. Pereira, right? Yep. Thank you. My apologies. Here from the University of Catholique in Louvain in Belgium, where he is a professor. Olivier has done a lot of great work on election systems, especially the Helios system, where he's done a great deal of development and was principal in getting it used in an election with, I think, 25,000 eligible voters, something like 5,000 people who actually voted for the university president there. So this took an extraordinary amount of work to make it happen, but this is the largest ever real use of a end-to-end verifiable voting system, and we're all very pleased about this. Olivier has also done a lot of work in related systems and making privacy better, and I think that's what we're going to hear about largely today. So, welcome.
Thank you very much for this very kind introduction. I will indeed talk about privacy in voting. Please feel free to interrupt me at any point if you find it useful. So this is joint work with David Bernhard, Véronique Cortier, Edouard Cuvelier, Peters and Bogdan Warinschi. So I would like to talk about privacy in general. It was introduced in most of our countries during the 19th century as a requirement for public elections in order to avoid this kind of situation with public voting where you have a lot of people strongly suggesting to voter to vote in one sense or another, and since the vote was public, they could just actually check what the voter was doing. So in many places during the 19th century, people decided to introduce secret ballot elections in order to prevent corruption and bribery. It has also some other benefits, but I'll come on that maybe at some later point. So we want to have secret ballots, but what does it mean? The first obvious thing with voting is that the secrecy of the ballot is not something that is just completely absolute. If all the voters vote in the same way, in most of the voting systems that are currently used, we will know that all voters supported the same candidate with 100% of the votes. And that's not seen as a breach of privacy from the voting system. So it's not something like an absolute privacy definition like we have for the security of an encryption scheme. We want something that is weaker. Another approach of defining the privacy of the votes would be inspired from the work on secure function evaluation. The idea would be then to say something like the voting system should not leak anything about the votes besides the outcome of the election as it's written in the bylaws. So that's certainly a good approach for defining the security of cryptographic voting. We would like to say more about privacy in the sense that we would like to see how much a voting system actually leaks when it's used in a normal way. We would like to know how much the outcome of the election actually leaks in terms of information about the votes. Another approach for defining vote privacy was proposed by Custos and al. At IEEE Security and Privacy last year. And they measured the privacy of a voting system as the maximum probability that an adversary has to be to win the game where he has to decide whether a voter voted in one way or in another way. So that looks like semantic security definition in CPA security definition for encryption. We don't require a negligible probability of winning the game there for that reason, essentially. But it seems that that definition is too strong in many cases. For instance, if you have approval voting on complex ballot, you have, I don't know, 50 choices. that makes a lot of different ballots, and you will not have enough voters to make sure that all of the possible ways of filling the ballots are represented. And if you use that definition in that context, this definition will just tell you have no privacy at all, which is not quite what we want. We want to say, okay, we have this set of ballots, and we still don't know which of those ballots was submitted by that voter. So we want metric should say that there is some amount of privacy left. What is it that we really want to measure in terms? Yeah.
Before you get into privacy, what's the election outcome? Is it that so-and-so won by a large majority and you stop counting? If there's 1,000 votes and after 700 votes you got 650, right, I can stop counting there and then in terms of making a decision, and then less information leaks.
It could be. It depends on how you decide to have the regulations. Typically, the election bylaws were required to say how many votes each of the candidates received.
Because I understand this write-in ballot is different. They only get counted if they have a chance of affecting the election.
Okay.
Okay, but
that might be part of the definition.
Numbers, or it can be who won it and by approximately what margin.
Yeah.
Changes that information that leaks.
Certainly. I will have examples on that line later.
But as long as we're stopping, I can't resist mentioning one of my favorite examples, which is an election that's almost unanimous except for one. Because in that case, that one person knows exactly how everybody voted, but nobody else is quite sure.
Exactly.
And that's accepted from the outcome.
Yeah, that's true. Okay, so we want to measure privacy for any voting system. So what's the kind of thing that we would like to know? So one first question that we may want to ask is, with what probability can my adversary guess my vote? So that's the kind of thing that we can measure with mean entropy. That might be a natural approach for that. Second question is, in how many ways can I pretend that I have voted? So if in case somebody wants to force me to vote in one way or another, I would like to know which amount of freedom I have into claiming that I voted in one way or another. So that's the kind of thing that is measured if you use Hartley entropy. So we seem to have at least here two natural questions and two answers that look like entropy seems to be an interesting direction. So we explored that direction. I will just introduce a few notations before coming to our definition. So we suppose that we have a distribution D for the honest votes. We may know that distribution or we may not know it. It will depend on the context. But if we know it, we can capture it. Then we have a target, which is what the adversary would like to learn about the honest votes. So the target is a function that starts from the support of the distribution of the honest votes and goes to something, whatever. It's what the adversary will try to guess. So one example would be, okay, the target of the adversary is to guess the votes of the ith voter. Another target of the adversary would be to say, I would like to know whether those two guys voted in the same way or not. Another target would be, I would like to know if the population in that specific area voted in that way rather than in any other way. So that's something extremely general. And then we have this function rho, that is any function that takes all the votes and provides the outcome. So that might be each of the candidates received that many votes, or it can be this guy is the winner. It can be a lot of things. And then eventually we have the view of the adversary, which is a random variable. We have one specific adversary. We have one distribution on the honest votes, and we have a specific protocol that we play for the election. So that captures the view of the adversary here. And from that, we propose a family of measures of privacy, which are as follows. So we have here a measure M with X, which can be a variant of that measure. I will come on that later. So we want to measure the amount of privacy on this specific target for this specific distribution of the honest votes and in that specific voting system. And we say that this is the minimum of amount of entropy taken on all possible adversaries that is left on the targets when the adversary has this view and also views the outcome of the election. So this fx is something that is left open for the moment, but really the idea is how much information do I have about the target given the view of the adversary? We take the worst possible adversary. So the question now is, how do we define this fx? General idea would be to say fx will be some sort of conditional Rayleigh entropy on A given B. That's very fuzzy. So let's go to maybe some more concrete examples. So here are possible choices. So if we go for Shannon entropy, that doesn't seem to lead to any practical interpretation. If we go for traditional conditional entropy, that doesn't seem to provide anything useful either. So one notion that seems to be informative is average mean entropy. That's a notion that comes from a paper by Dodis et al. Essentially, that gives you, expressed in bits, the probability that the adversary guesses the target. You just have the traditional mean entropy here, and you take the expectation here on all possible views that can happen on that side. Okay, so that's one measure. Another one that seems to lead to practical interpretation is what we call mean entropy. We still have mean entropy, but here we consider the worst possible view that is given to the adversary. So that captures the case where we would like to know the amount of privacy that the voters keep, even if all honest voters do the exact worst possible choice in terms of privacy. So if all the voters vote for the same candidate, we would like to know how much entropy is left on the target. So what's the probability that the adversary guesses his target in the worst possible case? A third possible notion is what we call mean Hartley entropy. So that's, again, a worst case. We take the minimum over all possible choices by the voters. But now we simply count the number of possible values that the target can take in this worst case. So an interesting thing of this measure is that it has no probability at all. It's just taking into account the support of the distribution, so the possible votes, essentially. But we do not need to assign any probability to any specific vote. So when this is not known, that's a convenient measure to use. Okay, so now let's see on simple examples the different feelings that we get from those three measures. So we'll take something extremely simple, approval voting, one single question, so I answer either yes or no, 0 or 1. 3 voters, I assume that they vote uniformly at random. And the target for the adversary is the choice of the first voter. So you would like to know how the first guy voted. And we consider 4 different tallying rules. So in the first case, the tally is just a constant. It's something that is independent of the choices of the voters. And in that case, whatever measure we take, as expected, we get 1 bit of entropy. There is 1 bit the voter choose uniformly between two different values. So 1 bit of entropy. Second thing is just saying who the winner is. So we tell whether there are more 1 choices than 0 choices, which is essentially what you proposed. Then we see a few changes. If we start from here, which is the easiest solution, we see that in terms of Hartley entropy, we still have 1 bit. Because if I know that I have more votes for 1 than votes for 0, there is still a possibility that the first voter voted either 1 or 0. The 2 remain options, so we'll still have 1 bit of mean Hartley entropy. If we go for the mean entropy, then we see that we have a substantial decrease. This is essentially because if I see that outcome, I have a fairly good probability of guessing how the first voter voted. What happens is that I have, if I know that there are more ones than zeros, I can see that there are essentially 3 possible ways of getting more ones than zeros that give a 1 vote for the first voter, and 1 single that gives a 0 vote for the first voter. So the 0.4 is essentially minus logarithm of 3 out of 4. And if we compute here for the average case, we obtain the same numbers through a different computation. So in the average case, I have one case where, actually this is just symmetric. We know who the winner is, and we do not know much more. And since this is completely symmetric, we have the same numbers on both sides. So the third tallying function is how many yes votes happened and how many no votes happened. So this time, the mean Hartley entropy becomes 0 because there is the case where everybody votes 1 or everybody votes 0. So since this is worst case, we have no entropy left on this side. And in terms of mean entropy, we have 0 as well for the same reason. There is a worst case in which I can guess with certainty. But now in the average case, I still have some entropy because there are cases where I cannot guess. I can guess, but I cannot be sure. So I keep some amount of entropy in that case, in the average case. And so eventually, this is the function that gives all the votes of everyone, and I have no entropy left anywhere. So these seem to correspond with our intuition, at least. So we can measure quite a lot of things. We can compare different tallying rules using this kind of metrics, see how they behave. And we actually decided to go for one practical example. We consider the Scantegrity voting system. So Scantegrity has been used in a municipal election in Takoma Park in Maryland in 2009, 2011. It's an end-to-end verifiable voting system. It's a paper-based voting system. So the ballots look like traditional paper ballots. You have bullets on which you indicate your choices. The only difference is that when you want to pick a candidate, you use those special pens that reveal some invisible ink. So when you select that candidate here, you will see appear some letters that make a code. And the idea is that this code is something that you should write down on a take-home receipt, and you will be able to use those codes to verify that your ballot is properly recorded, and there will be an audit trail that will allow you to verify that the outcome is correct. In those elections, what is required by the bylaw, the official outcome of the election is the number of votes that each of the candidates received. So that's one level of privacy that we may want to measure. But actually, if we look at the effect of using Scantegrity, we see that we have more information that is revealed. One thing that is revealed is that each individual ballot is revealed in the clear. So these are shuffled, so you do not know which ballot comes from who, but you see the ballots, essentially. A second thing that you can see is that you have those take-home receipts. So they are supposed to be something that you can show to everyone. The system is supposed to be receipt-free. So if you see someone with a certain number of codes on its receipt, you know how many bullets were filled by that person. So that gives you, again, a bit more information.
In Scantegrity, isn't it the case that the take-home receipt is filled out by hand, so a voter could add extra codes or not?
They could. They certainly could. I'm not sure that adding extra codes would be extremely effective because if you check on the bulletin board, you will see which code happen and do not happen. But you
can certainly eliminate some codes.
That would be.
You voted for fewer.
Yeah, you could. It's not part of the instructions, but you could. Yeah. Okay, so we did some analysis. We took the Takoma Park 2009 election data. I just have some numbers gathered here just to give a sense. There were 6 different wards. So I have 1st, 5th, and 6th, which are represented here. I just took 3 of them to show the number of voters differ quite a lot between the different wards. So if you take the 1st ward, we have 470 votes that have been collected. In the 5th ward, you only have 85 votes that have been collected. There were 2 questions in each ward, so question 0, question 1. And then we can check the official outcome. And we see that actually in all the wards, all candidates received at least 1 vote. So we have the maximum amount of entropy everywhere. 6 bits of entropy corresponds to 3 possible choices. 3.17 bits of entropy corresponds to 2 possible choices. You can rank the candidates, so that's why you have more possibilities than just for approval. And then you can wonder what's happening if you take a look at the receipts. And then we see that the amount of entropy decreases quite a lot. And in particular, we see that in the ward 5, for question 0, there is no entropy left. This actually means that for one of the voters at least, if that person shows her take-home receipt, we know how that person voted. Because essentially, that person is the only one to have filled a certain number of ballots on his ballot. So if we see the size of those ballots, it seems that normally we would not expect this to happen. But in practice, people really do not vote uniformly. So there are really specific ballots that happen all the time, and very few people vote differently of the others in those elections, at least. So I think it's an interesting thing to maybe do some routine evaluation of those entropy metrics on election data to see how much the privacy might be impacted by some maybe unexpected effect due to non-uniform voting ways or things like that. Okay. So that was for essentially the first part of my talk. Now, second part, I would like to talk about cryptographic voting. So our metrics now are just purely information theoretic.
Before we go into it, do you want to take some questions?
Sure.
I've got a few things that I'm trying to ask about. One is there a way of accounting for partial information? If I know how some of the voters voted, but not others, how does that figure into eventually? Like the example I gave with, I know the one voter who voted yes, then I know everybody else who voted no in that case. But if I have partial information, it might.
If you have that, essentially you will include this in the D.
Okay. I see. So that's your distribution. That's the view at that point.
Is it the view or is it D? Isn't that the view of the adversary more?
What you know in advance, actually it's not, if I understand properly your question, you know that some guy voted in one specific way. That's not given by the system. It's something that you know in advance or that is revealed outside of the system. So that's something that we would typically include in the distribution on the honest votes.
Okay. Another question that I had is another way that this could be done, I'm just trying to see how the two fit together, is you take an election and you take 2 voters who voted differently in some way, and you reveal their clear text votes, and you say, you ask an adversary whether an adversary has a chance substantially greater than 50%, say, of determining which voter cast which of those 2.
Okay.
That's just the sort of capture. You don't need to worry about the information given by the outcome. You're just looking at what the system reveals.
It will tell you something. It will not tell you the cases where you want to avoid signaling, for instance. You want to measure that there are 2 to 40 ways of filling the ballots and you have very few voters, so you would like to say, okay, I do not have 40 bits of entropy. So that part you will not have it captured. But your suggestion will actually come something inspired by this a bit later.
Oh, great.
Any other question? Okay. Okay, so now we would like to move to cryptographic voting. Yeah.
One thing, everything here applies to privacy of individual voters and threats to individual voters.
The target could be more than one individual voter.
Sorry?
The target could be anything.
Okay,
Or
because
examples.
there's lots of cases where the threats are to groups of voters.
Yes.
I recall Singapore spokesman, government spokesman saying, yes, it's okay, when the building votes the wrong way, we'll fix the elevators after the next war.
Indeed, that makes sense. But it could be captured. Yeah, I heard about stories in Sicily as well.
Sicily is spread individuals. After the Yom Kippur War, there was a rumor in the army that any battalion that had enough communist votes would be pulled out of Africa in a hurry. And it was very popular to be pulled out of Africa.
Okay. So, cryptographic voting protocols. I would like to consider a class of voting systems, probably the most common class of cryptographic voting schemes, which include Helios, for instance, which follow this general pattern. Strongly simplified, but that's the general idea. We have trustees, a set of trustees. They generate a public key, private key pair. They keep the private key for them. They send the public key, broadcast the public key. Then each of the voters take the public key, and then using some encryption mechanism, taken in a very broad sense, something that is essentially a ballot preparation protocol, they take the vote, they take the public key, and they produce an encrypted ballot, which might contain some zero-knowledge proofs or other stuffs. And they send that to the trustees. And then the trustee will run some tallying protocol. That can be also a lot of things. And they will publish the outcome of the election. So that's just the general idea of many schemes.
You can probably attribute that paradigm back to Schaum in '81, the original mixed network.
Okay, yeah, that makes sense. Okay, I should add him on top of the list. The problem if we want to apply our entropy measures on that is that we will just not get any privacy at all, because if we take any information theoretic entropy metric, we have an adversary who sees a public key and then an encryption of a vote using that public key. There is no entropy left on the votes from that. The vote is just completely determined from the ciphertext. So that's not quite useful. So for that reason, we decide to move to some computational analog of entropy. There are many ways of defining this that appear in the literature. We took one way. Essentially, we say that for some kind of measure of entropy, F, we have an amount of computational entropy that is at least R on the value A given B, if and only if there is some random variable B prime that is computationally indistinguishable of B, and we have at least R bits of entropy using the corresponding information theoretic entropy metric, but with the distribution B prime given to the adversary. So in particular, if you want to apply this definition to that example, we can say that there are at least R bits of entropy on the votes here, given this ciphertext, if there are at least R bits of entropy when the view of the adversary is actually an encryption of a constant instead of having an encryption of the votes, because traditional encryption schemes will make this indistinguishable of that. So we can then have computational analog of our previous metric. This is exactly the same as before, except that we have computational metric here and a C over there. So that's just a definition. The problem is that it seems much more complicated to evaluate a metric like this, essentially because we need to find or to define somehow this B prime. And that's something that you cannot just sample maybe, or it's more complicated. So what we would like to have is some convenient way of moving from computational entropy to traditional information theoretic entropy, and at the same time maybe removing all those stuffs that are part of the protocol. So we would like to get rid of the cryptography and say our protocol is good if we have an amount of computational entropy that matches the level of information theoretic entropy that is obtained when we just see the tally. So for that purpose, we decided to go for a classical cryptographic security game, which is something that looks maybe a bit more complicated, but it's much easier to use in cryptographic security proofs. So the game is as follows. We have an adversary, we have a challenger, or an oracle. This oracle chooses a private key, public key pair, just like in the actual voting protocol, and it chooses a bit beta. The goal of the adversary will be to guess that bit beta. So the first thing that the oracle does is send a public key to the adversary, like in a regular election. And then the adversary can do two different types of queries. So the first type of query is vote query. So these are essentially modeling the votes of the honest voters. Those vote queries contain two different votes, which is kind of in the direction of your intuition before. Now what the oracle will do with those two vote intentions here, he will run the normal ballot preparation procedure from the protocol. So he will produce two encrypted ballots. And then he will have two built-in boards, a built-in board 0 and a built-in board 1. And he will place those two ballots on the two corresponding built-in boards. But depending on the value of beta, the adversary will just see one of those two built-in boards. And so that's where the adversary sees something that is related to beta, and he needs to guess somehow which of the two built-in boards he sees. So that's one type of queries. Second type of query is ballot query. So here that somehow counts for the adversarial votes. The adversary can just produce whatever he wants, and maybe not following the ballot preparation rules, and sends those encrypted ballots that might just mean nothing at all, or could be computed from things that the adversary saws on the built-in board. He has a lot of freedom for that. And now the oracle will just apply the protocol to check whether this is a valid encrypted ballot, if there is something described in the protocol in terms of verification procedure. And if that is valid, he will post this B on the two built-in boards. Again, the adversary just sees the built-in board beta updated.
In the first case, the votes are prepared by the adversary?
Here?
Yeah.
No, by the oracle. These are, I vote for this candidate. These are clear votes, V0 and V1. And the oracle perform the encryption, computes proofs, and all those things. While here, this is a real ciphertext, and the proofs are in there. So essentially, in this case, the oracle knows what will be displayed on the built-in board. In that case, that might not be so clear. So we have the adversary can place those two queries many times in whichever order he wants. And then eventually, when he's done, he says, OK, I would like to see the tally. And now the oracle will just show the tally of the built-in board 0, always the same. So that's essentially prevents trivial distinctions that could happen with the adversary. I don't know, we might be willing to say, I want to see the tally beta. But if we do that with just one vote query with two different votes from the tally, the adversary would be able to know the beta. So he sees one outcome. And we say that the voting system is secure, offers privacy, if the probability that the adversary guesses beta is essentially 1/2 plus something negligible. So that looks like a traditional cryptographic game. more convenient to prove using cryptographic tools. And we can actually show that if a cryptographic protocol satisfies that definition, then we have what we expected. So what we expected more formally was something like this. Consider a tallying function rho. So that's the outcome that is expected to be computed from the votes. And from this, we have an ideal voting protocol in which voters submit their votes perfectly privately to the trustee, and the trustee reveals a row of all the votes. So that's the ideal voting system. And what we can prove is that if you have a voting protocol pi that satisfies our cryptographic game before, then for any target and any distribution, the metric that we have on this is equal to the metric if we evaluate just on the outcome of the election, so to the ideal protocol. So no cryptography on that side, which is what we wanted to achieve. We still have something that is computational here. In most practical cases, the computational will be just equal to the purely information theoretic thing. We have it because the tallying function, we did not say anything about it. It might be something that in itself contains crazy cryptographic stuffs. And in that case, we still have something that is computational. But for most practical tallying functions, that will just be the information theoretic version. OK. So it's 2:10. Yeah, maybe I can. Now, the next natural question will be to say, OK, we have this cryptographic game. We would like to know whether a voting system that follows this line satisfies the cryptographic game. So what do we need to do, essentially in terms of encryption at this step, to have it that no adversary will be able to win here? So the first intuition might be, OK, we just have 2 votes sent. The adversary needs to guess which one. This looks like in CPA security or something like that. So maybe semantic security would be good enough. Actually, it's not the case. So here is the kind of thing that could happen. First, the adversary queries for a vote for 0, then and a vote for 1. So what the adversary sees on the bulletin board is an encryption of either 0 or 1, depending on the bit beta. And now the adversary says, OK, I will just take that ciphertext. I don't know what is encrypted here, but I will just use it in a ballot query. And now I ask for the tally. And we can check that the tally will be equal to beta. So that's certainly something we want to prevent. How do we prevent this? One way would be to say the authorities should just reject all duplicate ciphertext. We do not want people to take a ciphertext and resubmit it. The problem is if we use just traditional in CP encryption scheme, it might very well be homomorphic, in which case people can take ciphertext and do some re-encryption procedure and transform one ciphertext into another encryption of the same thing, and that would not be detectable. So we want to have something stronger from the encryption scheme. We want to make sure that people cannot transform a ciphertext that they see. And then if we are sure that they cannot transform the ciphertext that they see, we can apply a rule that says we reject the duplicates, because they're the only thing that is left. So what we want is some form of non-malleability from the encryption scheme. So other people looked at this before, and in at least 2 different papers, recent papers, the conclusion was that if you use in CCA2 encryption, which is a fairly strong form of non-malleability, we are good. That's OK, that's good news. At least we have a notion that we know how to have satisfied by an encryption scheme. And we have a security proof for that. The difficulty is that if you look at most of the actually deployed or most of the protocols that have been proposed for doing voting using the lines, the approach I presented before, that people use an in-CPA encryption scheme, exponential gamma or pi encryption. And then they use sigma proof of knowledge of the plain text, usually something that is made non-interactive using the Fiat-Shamir heuristic. The problem if we use that is that we do not know how to prove that this yields in CCA2 encryption. This is well explained in a paper by Shoup and Gennaro, Journal of Cryptology 2002. There are some kinds of proof in unusual models, I would say. But we do not know how to prove that this provides in CCA2 security in any common model. So there are two approaches to that. Either we say, okay, let's change all those schemes and move to a real in CCA2 scheme. Or let's check whether this is actually necessary. Can't we have some weaker form of non-malleability? And what we proved is that actually we do not need in CCA2 encryption NMCPA encryption, which is a much weaker form of non-malleability, is actually good enough. And we also proved that if the strategy of the authorities is to reject exact copies of ballots, then that form of non-malleability is actually necessary as well. So NMCPA is essentially a characterization of what is needed to submit ballots in a voting system. So we have a weaker notion of non-malleability. And then the good news is that it's much easier now to show that if we have an NCPA encryption scheme, El Gamal, Paye, or whatever, and then we have those traditional sigma proofs made non-interactive using Fiat-Shamir, then we have an NMCPA security. So the conclusion of that, or a corollary of that for practical encryption voting scheme, if we take Helios, for instance, is that if we do the Fiat-Shamir transform slightly differently from the way it's done there, but it's really a minimal change, then the ballot submission security procedure used in Helios satisfies the cryptographic game that I presented before. So, okay, that's what I wanted to say about cryptographic privacy.
You could mention what happens if that transform is not done.
Actually, if in the way it's done, not all the expected inputs are part of the input of the hash function that is used in the Fiat-Shamir transform. And actually, an impact of that is that the zero-knowledge proofs that are used there are not sound, and that essentially breaks the verifiability of the scheme. So it's really an important thing to do that change in Helios. It's not that we cannot prove the security of the scheme, it's just that the scheme there is insecure and we need to change it to have that proof working.
So is that going to come up in another spec soon for Helios? Is this planned?
Exactly.
Okay.
It's on the way.
Good. Update AFON when it...
Thank you.
And it reveals a vulnerability in previous uses of Helios.
Absolutely, yeah. Yeah, it's very interesting.
Okay, one last thing I wanted to discuss is the balance between privacy and verifiability. So, like Josh said, I have been involved in a fair amount of universally verifiable elections and discussed it with a lot of people who were considering adopting end-to-end verifiable voting systems. And one of the big concerns that essentially made some people at least not go for universally verifiable encryption was the presence of a built-in board. So if you take the first ideas that the people have when they want to go for an internet voting system, for instance, is okay, we'll just encrypt our votes, we'll send our votes to a server, and the server will announce the tally. And now you would like to make that verifiable. Okay, that's good. And now you also would like to display all the ciphertext on a web page. Why would you want to do that? Because that's what provides verifiability. From those ciphertexts, we can verify that the outcome matches all the ballots, encrypted ballots that have been submitted by the people. Oh, no, we don't want that, because at some point your cryptography will be broken or the machines will become too powerful. Everyone will be able to decrypt everything. And we do not want the voting system to just provide a vector that makes it easy for everyone to just download all the ciphertext and wait until some cryptographic breakthrough happens and allows to just decrypt everything, or wait until there is enough computational power to just do some kind of brute force attack. So one question that came there is, okay, can we now offer a universally verifiable voting system without impacting the privacy of the original thing that people have in mind? Can we just add verifiability as a new feature that doesn't impact the other previous features of the scheme? So one idea for doing that would be as follows. We consider first the private built-in board. You can view that private built-in board as essentially the voting server. It's where the people submit their encrypted ballots. And that's essentially the view that people have for the non-verifiable voting system. We have computational privacy with respect to these very selected authorities who control the voting server. Now we would like to add this public built-in board. That's what will be used for universal verifiability. But now there do not need to be any way of actually computing the outcome of the election. We can just have something that allows verifying the outcome of the election. So we could have information theoretic privacy on that public built-in board. In that way, the public built-in board just contains something that is statistically independent of the actual votes. In practice, if we have information theoretic privacy on the built-in board, that means that we will also have computational verifiability of this board. But that seems much less dangerous, because it means that if the cryptography is broken in 20 years, people will be able to forge proofs or claim that the public built-in board indicates another winner. But nobody will believe that, because the cryptographic proofs are not sound anymore after 20 years. So that seems much less damaging than being able to say, okay, you voted for that guy, and that guy happened to have, I don't know, what bad story could happen. So to that purpose, we proposed the use of a new cryptographic primitive, which we called commitment consistent encryption. So commitment consistent encryption scheme is essentially a traditional threshold encryption scheme that comes with two extra functions. The first function, extract C, takes a ciphertext, an encryption of a vote, and extracts from that ciphertext a commitment on that exact vote. Typically, the commitment will be something perfectly hiding. The second feature of the encryption scheme is that we have an extract E function that also takes a ciphertext, and that gives you an opening of the commitment that you got there that is consistent with the initial voter intent, so the message that the voter encrypted. So just to have an immediate idea on how to build something like that, one way will be to say, okay, I will take an encryption and a commitment scheme. I will generate two key pairs with the public key encryption scheme. I will generate one key from the commitment scheme. And now when I want to encrypt a message or a vote, I will use the commitment scheme to compute a commitment and the auxiliary value that is needed for opening the commitment. And then I will use my two encryption keys to encrypt the actual message and to encrypt the auxiliary value that is needed for opening. And so the ciphertext is now made of the commitments and the two encryptions. So that's a simple way of building this, not a very efficient way of building this, but it actually works.
Do we know that the two encryption schemes have to be different, or is it just necessary for the proof? Does it fail if we use the same public key, or the same Jenny once?
Certainly easier for the proof if they are different. I did not check. It might work with the same key. Yeah, should check. So if we have this commitment-consistent encryption scheme, then we can vote as follows. We take the general idea of the voting scheme I presented before. We still have the same first step, generation of the public key for this commitment-consistent encryption. The voters now encrypt their votes using that commitment-consistent encryption scheme. And now, for verifiability, the authorities will not publish the whole ciphertext. They will extract the commitment and publish the commitment part. And now I will consider two different ways of verifiable ways of computing the tally, to the two most common ways. One is homomorphic tallying. So the idea is to take all the ciphertext, compute the product of all the ciphertext. That provides an encryption of the outcome of the election, and we decrypt that outcome. So we can do exactly that thing. And if the commitment scheme is homomorphic, we will just let the auditors compute the product of all the commitments. And when we decrypt the product of all those ciphertexts, we will get an opening for the product of those commitments. So now, if we take the traditional approach, what the authorities need to do is to compute a zero-knowledge proof that they actually decrypt the product of the ciphertext. Here we have something that is simpler. We just need to reveal the opening of the commitment, no proof needed. And now the security follows from the binding property of the encryption scheme. Other approach, it's mixed net-based tallying. So here, the idea is that the authorities take all those ciphertexts here, and then they do a verifiable shuffle of all those ciphertexts, and they decrypt the outcome of this shuffle. So we can do exactly that here. We include verifiable shuffle proofs for the commitments. We use statistical zero-knowledge proofs of the correctness of the shuffle that I would say most of the classical verifiable shuffle comes with statistical zero-knowledge proof, so that's not an obstacle. And now again, we open the shuffled commitments, and the verifiability follows from the binding property of the commitments. So how to build more efficient commitment-consistent encryption schemes? One extremely useful tool that we found were what people call structure-preserving commitment schemes. You might have seen this paper over there at Eurocrypt this year. These are nice commitment schemes that have things that makes life much easier and computation much more efficient. So these are commitment schemes that are based on elliptic curve groups that support pairings. In our case, we go for symmetric pairings, which are the simplest ones. So we have two groups, G1, G2, and a bilinear map from G1 and G2 to GT. And now here is an example of a commitment scheme that works along those lines. For the public key, we take one generator of the first group, two random generators of the second group. And when we want to commit on a vote, the commitment part is actually computed just like a Peterson commitment. The big difference is that now the opening is not made of R. The opening is made of G to the R. And that's the convenient thing, is that now it's a group element. And that's much simpler to mix with encryption, to mix with Sigma protocols. So all the zero-knowledge proofs become very straightforward when we use this. So when committing, we do not need to perform any commitments. So the voters do not need to compute any commitments. It's just part of the audit. If you want to check that the outcome is correct, that you need to compute some pairings to make sure that this is working fine. In terms of security, the binding property of this scheme is implied by the decisional Diffie-Hellman assumption in the two groups. Actually, weaker computational assumptions are needed, but since we will mix this with L-gamma later, everything holds if we have DDH. So here is the first of our two schemes. This one is designed for homomorphic tallying, so it means that we need to have something that is additively homomorphic, and also that we can tolerate something where the decryption procedure is not efficient, because what we will need to decrypt is the outcome of election, and that's not something that is too big. So we can do exhaustive search, for instance, to find it, which is what we have to do with exponential L-gamma anyway. So 2 generators of the 2 groups selected randomly. And the private key is actually the discrete logarithm of G1 in the base G. So the private key is X1. And now, very simple, the commitment is exactly what I presented in the previous slide. The opening was G to the R, and so we use this L-gamma key to encrypt G to the R, so traditional L-gamma encryption. So the commitment is this part, that's what is published. And for decryption, like I said, we need to extract some discrete logarithm in GT. That can be done efficiently by exhaustive search. Okay, so we have all the properties that we expect. This is in CPA, so that means that we can add the sigma proof to make it an MCPA and have all the proofs I presented before working well. It's compatible with traditional Schnorr-style protocols. Okay. So maybe I will go faster on this one. So we have a second encryption scheme that is more designed for mixed-net-based tallying. So the difference now is that we have a large message space. We want to be able to encrypt whatever we want. But we do not need to have an additive homomorphic law. We just need to be able to do re-encryption, so we just need to have a neutral. And so by tweaking the commitment scheme, we have something that is still quite similar, a mix of L-gamma and commitments, same properties as before. So we consider the efficiency of those solutions. So one previous solution used in a different context, but also for voting, but slightly differently, was based on Peters and Bogdan. So you can see that if we take our 2 encryption schemes compared to the solution there, we have roughly a factor of 100 in terms of efficiency benefits. Now I think that that's probably not the most important benefit. I think the most important benefit of those solutions compared to that one is that the threshold key generation procedure for PIA is something that is quite complex. Here we do everything in prime order groups, so we have a much simpler key generation procedure. From a practical point of view, that's important. So to conclude, we have discussed information theoretic and computational definitions of privacy for voting. We showed a cryptographic game that can be used to bridge the 2 notions fairly easily. We identified an MCPA security as the necessary and sufficient notion that an encryption scheme must satisfy for submitting ballots. We showed that the traditional approach of using an NCPA homomorphic encryption scheme with a Sigma protocol made non-interactive using Fiat-Shamir can offer an MCPA security. And then eventually we proposed new encryption scheme that proposed, we think, an interesting compromise between information theoretic and computational privacy. Any more questions? Yes?
So just the previous slide at the bottom had some numbers on Java, because essentially how much of that in dollars? Okay. 1 second. Okay.
Yeah, in JavaScript. In JavaScript, not Java.
Sorry?
In JavaScript.
Sorry, JavaScript. Okay, and you expect it to be 50 milliseconds if used that hard. Okay.
Yeah, and by doing a master student at UCL is implementing this, and this is just by using standard library, and if we just try to implement it more efficiently, we can have it much faster.
Okay.
Thank you.
Well, you managed to weave